We mentioned earlier the interplay between angles and lengths in terms of Pythagoras' theorem, which is a theorem giving equivalence between two conditions, one in terms of angles and the other in terms of lengths. In linear algebra, this interplay is nicely captured in terms of an inner product which induces a norm. Thus, if the inner product is written like this, x, y, then the norm that it induces is this positive square root or non-negative square root of inner product of x with itself. Now, norms are very useful. Based on their various uses, mathematicians have extracted the most commonly used properties of norms. For all these properties, V is a vector space over a field F, which has to be either R or C when we talk about norms and inner products. The norm is a function from V to R. Irrespective of whether you take the field to be R or C, this is always R. The properties are, number one, for any vector, we must have its length greater than or equal to 0, which is sort of our day-to-day experience. You cannot draw an arrow with negative length. And if it is equal to 0, that will necessarily imply that the vector must be the null vector. The second property says if you take a vector and multiply it with a scalar, in that case the length of the vector will be scaled by basically that scalar, but this alpha comes out as mod alpha. Remember, alpha may be either a real number or a complex number. If it is a real number, then this is interpreted as absolute value. If it is a complex number, it is interpreted as the modulus. The third property, which is extremely useful, is called the triangle inequality, which says that if you take any two vectors x and y in V, in that case, norm of x plus y is less than or equal to norm of x plus norm of y. In order to understand why it is called the triangle inequality, it will help to think in terms of a little diagram. Suppose that I denote the vector x by this arrow and y by this arrow. When I arrange them in this way, one after another, I get this, which is x plus y. And from our usual Euclidean geometry result, we know that for a triangle, the length of any side must be less than or equal to length of the other two sides, the sum of the lengths of the other two sides. So in this case, length of this is less than or equal to length of these plus length of these, and hence the name triangle inequality. Now, proving all these things are not very difficult, especially the first one is already part of the definition of an inner product. Remember, our norm that we are talking about is given by this. It is the non-negative square root of x plus x. So, from the very property of inner product, you get the first one. Similarly, for the second one, the third one will require quite a bit of work that we shall take up a bit later in this video. Now, these properties cover a vast majority of applications of norms, and so mathematicians have thought about defining the concept of norm independently of any inner product by using these very properties as the definition, and this gives rise to definition 7.3.1 in the book. So there we start with the vector space, and we say that if we have a function from V to R that satisfies all these three properties, then we shall call this function a norm. Now we know that inner products induce a norm. Now that we have a definition of norms independent of inner products, we can ask the opposite question. That is, given a norm, does there exist an inner product which will induce it? The answer is not always. That is, there are norms that are not induced by any possible inner product. The book gives a few such examples, but those norms are very rarely used in linear algebra with finite dimensional vector spaces, So in this video, we shall review those norms only briefly. These examples are either over Rn or over Cn. They are given in example 7.3.5 and 7.3.6 in the book. The first is a family of norms called the LP norms, and it is defined like this. You start with a vector either in Rn or Cn with components xi, then you define this quantity. You take their absolute value, remember absolute value in case of real number, modulus in case of complex numbers, raise them to power p, where p is something greater than or equal to 1, and then add them and then take the pth root. This is very much like the usual norm that we work with, except that there we take p equal to 2. We square them and then we take the square root. Now if you allow p to go to infinity, you can show that this thing will actually have a limit, and that is what is called the L infinity norm, which is a very simple definition. You look at the absolute values of all the xi and then merely pick the maximum of them. Now we need quite a bit of machinery to prove that these two things are indeed norms according to the definition that we gave just now. The book develops this machinery in Theorem 7.3.3, Holder inequality, and Theorem 7.3.4, Minkowski inequality. But as most of these norms are not induced by any inner products, as a result, they have very little use in finite dimensional vector spaces, so we shall not discuss these theorems in these videos. Indeed, among all these, only one norm is induced by an inner product, and it is the L2 norm. This is our familiar norm induced by the usual dot product. But how did we know that the other LP norms or the L infinity norms are not induced by an inner product? This theorem, Theorem 7.3.11, helps us to do that. This is called the Parallelogram Law. It says that a norm is induced by some inner product if and only if for all xy this equality holds. It is called the Parallelogram Law because it has a nice interpretation in terms of parallelograms for R2 or R3. So I take two vectors x and y. In that case, x plus y according to the Parallelogram Law is this. Similarly, x minus y according to the triangle rule is this. So it says that if I add the squared lengths of the two diagonals of a parallelogram, then I get the squared things. So the sum of the squared lengths of all the sides, because this is squared norm of x, squared norm of y, this is also squared norm of x, and this is also squared norm of y. So that's basically a geometric theorem. The non-trivial fact is that you actually have an if and only relationship. Now we shall not explore this particular theorem any further, except that mentioning if some particular given norm fails this condition for some x and y, then you immediately know it cannot be induced by an inner product, and that is how we know that all the other LP norms except p equal to 2 and the L infinity norm, they are not induced by any inner product. However, other than this, this theorem has hardly any use in linear algebra. So far we have not proved the triangle inequality. Now we are going to prove that in the next video.